Okay, so bear with me here. This is the last of the three videos that I want to use to replace the class on the 14th. And here I want to talk about roots of complex numbers. By that I mean things like square roots of complex numbers, cube roots, fourth roots, fifth roots, sixth roots, etc. Um, and one thing to say is that, don't get totally twisted around the idea of the use of the word roots here. We've also used the word roots to refer to the zeros of polynomials, places where when you stick these numbers into a polynomial expression, you get out zero. And these are related concepts, but they're not exactly the same. We're going to see, though, it's going to play an important role in the story that we're going to talk about here. Okay, so yeah, let's go here. First thing that I want to talk about is an element of redundancy that exists in the polar form for complex numbers. So one place to start, of course, is with the most important equation that we've talked about so far in complex in this class, Euler's identity, which tells us that what does it say? It says e to the I z is equal to cosine z plus I sine z. And this beautiful equation is true for all complex numbers z. Now, one thing to emphasize is that if z happens to be a real number, then we know something from trigonometry about these functions, cosine and sine. If z is a real number, we know that these functions are 2 pi periodic, meaning that we can shift the value of z by 2 pi and not affect either cosine or sine. Okay? So what does that mean for the polar form of a complex number? Like, let's suppose that we start with z being equal to r times e to the I theta. Theta here is a real number. It's the measure of an angle, right, with respect to the positive real axis in the complex plane. And what that fact that I just elaborated on, that I just explained, what that means is that I can shift theta by multiples of 2 pi in the following way. That this is equal to, in particular, r times e to the I theta plus 2 pi, or r e to the I theta plus 4 pi. And we can keep going like this. This is like going around the circle a full revolution and returning to where you are, or going around the circle a full 2 revolutions and returning where you are. Or you can go backwards around the circle, clockwise around the circle, a full 2 pi radians. So for example, r e to the I theta minus 2 pi. Same number. This is also the same as r e to the I theta minus 4 pi. Same number. All of these numbers, in fact, are equal to each other. They're all different polar representations of the same complex number. We want to unify them, we can, like r e to the I theta plus 2 pi n, where n is an integer, n in the integers. The integers are denoted with that fancy z there. And don't forget what the integers are. They are things like -3, -2, -1, 0, 1, 2, etc. Yeah? Okay. Great. So that's the redundancy or the ambiguity in the polar form representation of a number. If we want to discard or we want to shed ourselves of the possibility of redundancy, we can do the following move. We can, so to eliminate redundancy, require that theta be in the interval from 0 to 2 pi, right? If we fix if we require rather theta to live in this interval, then we won't get this kind of redundancy that comes about by the 2 pi periodicity of cosine and sine. It's like going through one full wavelength, but no more of cosine and sine. Does that make sense? Later, we'll use this insight to try to understand the geometry of the exponential function. The way that I would put it right now, and I'll let you just think about this statement, is that the complex exponential e to the z is 2 pi I periodic. Yeah? 2 pi I periodic. Meaning that we can add arbitrary multiples of 2 pi I to z, and we won't change the value of the exponential function. This is very interesting, and actually it's something that we saw when we were talking about the effect of the exponential mapping on the imaginary axis, because that imaginary axis wraps around the unit circle infinitely many times. To do one full wraparound takes 2 pi I. You have to have 2 pi I's worth of the imaginary axis to go once around that unit circle. Hopefully something like this makes sense to you. It makes sense in my head. We'll explain more later, okay? But for now, we want to use this ambiguity to help us find roots, nth roots of complex numbers. So nth roots of complex numbers, let's say W and C. Okay, so first of all, what do I mean by an nth root? So definition. An nth root of Z. Actually, let me say an nth root of W. Sorry, an nth root of W, where n is going to be a natural number, like not zero though. 1, 2, 3, etc. Okay, is a number Z. Such that Z to the n is equal to W. Okay, so in other words, it's a number which when you raise it to the nth power, you get W. Okay, and we know this from the basics of our mathematics education, right? So for example, as an example, the second roots, which nobody calls the second roots, also we call these aka square roots of, let's say, 17 are plus and minus square root of 17. This is very confusing because there are two square roots of 17. They are namely plus and minus the square root of 17. So then what's the square root of 17? The square root of 17 is the positive square root of 17. It's the non-negative square root of 17. This is oftentimes a cause for confusion. Sometimes people think that the square root of 17, this quantity, is two things at once. No. It is only one thing. It is the positive number whose square is 17. We call that the square root. And if we want to emphasize that it's the square root, sometimes we might say it's the principal square root, okay? But if we want to talk about all square roots of 17, well, there's two of them. There's plus and minus square root of 17. There's plus square root of 17, and then there's the negative of that. Okay, I'm not sure if any of that made sense to you, but it's something you got to come to grips with, because I want to make the following comment. If you look at z to the n equaling w, which is the equation which defines z being an nth root of w, then you can subtract w from both sides, and you get this equation. In other words, to find nth roots of w is the same as finding roots of the polynomial z to the n minus w. Finding nth roots of w is the same as finding same as finding roots of the polynomial z to the n minus w. That's a polynomial there in z of degree n. So by the fundamental theorem of algebra, there are n nth roots. Right? The fundamental theorem of algebra tells us that this degree n polynomial here must have n roots over the complex numbers. Each of those n roots are going to be nth roots of w. They're going to be numbers which, when raised to the nth power, give us w. Okay, so the question becomes, how do we find these nth roots? That's what I want to ask and try to answer here. Now, I could try to be fully general about this, but it gets quite involved. I think you're going to get the idea of how I'm going to put all of these various parts together with an example. Okay, so let's just run through a very specific example. Let's try to find, how about the fifth roots? The fifth roots of some complex number. Let's take 3i. Okay, so 3i is a complex number. I want to find all numbers z, which when raised to the fifth power, so z to the fifth, is equal to 3i. That's what I'm trying to do here. If you like, I'm trying to find this the roots of the polynomial z to the fifth minus 3i. Yeah, the degree 5 polynomial. Okay, how to do this? Well, first thing, let's just note how this example problem here is in compliance with other stuff. What's playing the role of n here? 5. Okay, just think with your thinky brain. You should be thinking something like n here is 5, n is 5, and w, the thing that we're trying to take the nth root of here, is 3i. Okay, just organize your thoughts a little bit so you have some clarity. Okay, cool. Okay, well, how are we going to do this? I think a good first move is to imagine, let me write this. We want to solve z to the fifth equals 3i, right? Such solutions to this equation are the fifth roots of 3i. Okay. The polar form. Well, let me say it like this. So let's say that the polar form. Suppose the polar form. Write the polar form of z. And say that this is equal to r times e to the I theta. Okay? Then this equation here, z to the fifth times e equals 3i, this equation becomes r times e to the I theta raised to the fifth power is equal to 3i. Now, I'm also going to write the polar form of 3i. 3 is the modulus of 3i. You'll be unsurprised to find out. And what is the angle that 3i makes with respect to the positive real axis? That's pi over 2. So we can rewrite 3i as 3 times e to the I times pi over 2. Is that sensible? Massaging the left-hand side a little bit more, I'm going to take r to the fifth power. And then, so that's me raising this to the fifth power. And then I'm going to raise e to the I theta to the fifth power. But by rules of exponent, that just becomes e to the I times 5 theta. And this is 3e to the I pi over 2. Now, first, let's compare moduli. We have r to the fifth. We want that to be 3. We want r to the fifth equal 3. That's comparing moduli, which means, of course, that we can take r to be equal to the fifth root of 3. Three to the 1/5. That's a number that you can stick in your calculator. I have no idea what the fifth root of 3 is, but it's some number. Okay, great. We also want the angles to agree. So I'm looking at now this angle theta, or the angle of the left-hand side. The angle of this side is 5 theta, yeah? 5 theta. But on the other side, we have pi over 2, yes? So we want that 5 theta be equal to pi over 2. But here's where the ambiguity in the polar form comes in. Because we don't just need to take, or we don't, we could also take not just 5 theta to be pi over 2. What if we took 5 theta to be pi over 2 plus 2 pi? In other words, we add 2 pi to this. And what if we added 4 pi? And what if we added 6 pi? Sorry. What if we added 6 pi? And what if we added 8 pi? Okay? So in other words, 5 theta could be equal to any one of these 5 different angles. And if we can figure out, so we can very easily figure out on the basis of this, the possible values of theta. Now, crucially, okay, why did I stop at 5? Why didn't I keep going? Why didn't I write pi over 2 plus 10 pi, and pi over 2 plus 12 pi, and pi over 2 plus 14 pi, etc.? Well, it's because by the fundamental theorem of algebra, which we haven't proven, by the way, but by the fundamental theorem of algebra, we know that there are n nth roots of w. Exactly n nth roots of w. There are exactly n roots of this degree n polynomial. And so we know that there are not at most, not at least, there are exactly 5 nth roots of 3. So I only need to write 5 of these numbers. And if I'm writing down 5 different numbers, then I win, right? If these are 5 different numbers, I know that those 5 different numbers have to be the 5 fifth roots of, in this case, 3i. Sorry, have I been saying that right? The 5 fifth roots of 3i. So this is an easy thing to solve. It's just like solving 5 8th grade problems. I'm going to add, well, before I solve the 8th grade problem, maybe I'll simplify these fractions a little bit. This is pi over 2. What is this one? So I think that's 5 pi over 2. Because 2 pi is 4 pi over 2, common denominator, right? And then it's just me adding, so I think this goes 9 pi over 2, and then 13 pi over 2, and then this one, 17 pi over 2. Yeah? So I want 5 times theta to be equal to one of these 5 numbers. So therefore, just dividing both sides by 5, I learned that I want theta to be one of these 5 numbers. So if I divide pi over 2 by 5, I get pi over 10. If I divide pi over 2 by 5 pi over 2 by 5, I get pi over 2. 9 pi over 2 by 10, 9 pi over 10, 13 pi over 10, and finally 17 pi over 10. Okay? So I have this factoid about r for z. Remember what r and theta are. R and theta are the bits of the polar form for z. And z is my 5th root of 3i. So I learned that z, in the end, z is going to be one of 5 things. You ready? It's going to be 3 to the 1/5 times e to the I pi over 10. I'm claiming, and I'm right, that that's a 5th root of 3i. It could also be 3 to the 1/5 times e to the I pi over 2. that's also a fifth root of 3i. Yeah, it is. Oh, and well, let me before I get there. Next one, 3 to the 1/5 e to the I. Is that a 9? It is 9 pi over 10. 3 to the 1/5 e to the I 13 pi over 10. And finally, 3 to the 1/5 e to the I 17 pi over 10. Okay? Now, I want to show you something here. Let's think about this number just real fast, okay? What's e to the I pi over 2? So think, a pi over 2 past, I think that's I, yeah? I think that's I. So this ends up being 3 to the 1/5 times I, right? And it's hard not to notice that this number 3 to the 1/5 keeps making an appearance here. And not only that, but because we've talked about it, that these exponentials here, like this one and that one and that one and that one and that one and this thing here, these are all on the unit circle. So if the modulus is what I'm trying to get at is the modulus of all 5 of these fifth roots of 3i live on a circle, and it's a circle of radius 3 to the 1/5 power. Okay, I'm going to draw these roots for you. And I'm going to do this by first drawing the circle of radius 3 to the 1/5. Shoot, this doesn't look right to me. Hold on, just bear with me. I wonder if I can do it small first. Like this, and then make it bigger. Like that. Okay. All right, there we go. There's a circle. Let's make this blue. I don't know why the little red dots appeared there. Okay. All right. A little imperfection in my picture here. Now we have 3 to the 1/5 I, and I want you to imagine that this is the circle of radius 3 to the 1/5. So this root right here is going to correspond to this point way up here, right? Okay. Now, how do we get from this root, which is right here, to this one? Because I, remember, is e to the I pi over 2. What is the angle I need to rotate around this unit circle in order to get to 9 pi over 10? So pi over 2 is 5 pi over 10, right? Pi over 2 is the same thing as 5 pi over 10. And I want to get to 9 pi over 10, so I have to shift over by 4 pi over 10. Or this is another way of writing 2 pi over 5. Oh, interesting. 2 pi over 5. And this will take me to 9 pi over 10. So that's going to be like somewhere out over here. All right. I'm going to go, in other words, if it's 2 pi over 5, it's like I'm going 1/5 of a full rotation around the circle. How do I go from 9 pi over 10 to 13 pi over 10? It's another 4 pi over 10. 4 pi over 10 is 2 pi over 5. It's another 1/5 of a revolution. So if I go another 1/5 of the revolution around, I'm going to end up here. If I keep going, I get something like this, and then something like this. And then if I keep going again, I'm going to return back to where I am. In other words, I get the vertices of a perfect pentagon. And I'm going to be really careful not to draw something satanic. Because in this day and age, we're all so sensitive, okay? Sensitive to symbols of evil, okay? And I think it's important that I not go there. So I won't. This is not a symbol of hatred here that I'm drawing. This is a pentagon. And in fact, it's a regular pentagon. And what could be more beautiful than that? Heavenly, godlike, okay? It's gorgeous, right? And in fact, so often, okay, the roots of numbers ends up having this kind of symmetry in the complex plane. Notice that though the calculation that we made took advantage of the ambiguity that's in the polar form. Okay, this is all very fun, but that's enough for today. This has already gone on longer than I thought it would. Very good. See you all next time. Bye.